In this video, we're going to talk about color and sight, so kind of these aspects of optics that are more to the kind of day-to-day, what do you experience? So for color, color is how the brain interprets different wavelengths or frequencies. So red light, what you see as red is the light that we can see that is the longest wavelength and lowest frequency. What you see as violet is the shortest wavelength, highest frequency. And this violet color is actually, when we say that in terms of light, we're talking about, sorry, not deep violet, deep blue. The kind of purpley that you get with mixing red and blue, that does sort of show up in the rainbow at the very end, but that's a more nuanced aspect of some other stuff that we're not going to worry about right here. But a rainbow is a separation of light by frequency or by wavelength, because again, those two are related. Right, higher frequency, lower wavelength, lower frequency, higher wavelength. And so every color that you see in the rainbow are all the colors that exist as a frequency of light. So that shows you the entire visible spectrum from that red, again, to that deep blue. So you'll have reds going into oranges, going into yellows, going into greens, going into kind of cyans, going into blues, going into like deep, deep, deep dark blue. Any color that you don't see in a rainbow does not exist as a single frequency of light. And what that means we'll get into in this next slide. But in some sense, the rainbow is all of the quote-unquote real colors, meaning colors that you can like create as like a single type of light. So now how does sight work? Well, sight works by having light focused on the back of the eye by the lens of your eye. So in your eye, you've got a lens, and it's basically taking in light from all around and making a real image on the back of your eye. Then the cells, and specifically if you remember from biology, those are going to be your cones and rods. We're going to talk specifically about cones, which can see colored light. They activate. So if certain light is hitting your eyes, they say, oh, I'm detecting this kind of light, or I'm detecting a lot of this light, or I'm detecting a little of this light. And in particular, humans are sensitive to red, green, and blue light. We are most sensitive to those because we have cones that are primarily tuned to picking up red light, cones that are primarily tuned to picking up green light, and cones that are primarily tuned to picking up blue light. These cones in turn send a signal to the brain, and then the brain interprets the signal as a picture. And so let's get into some of the details of that. So if we come here, what the back of your eye kind of looks like, it's not colored like this, but this is showing you the cells. So all around the outside of your eye, or around the outside of the back of the eye, imagine this is a bunch of circles. There's a bunch of cells that we call rods, and these don't detect color, they just detect light in the visible spectrum. So if light is hitting these, they'll light up, or they'll say like, oh, we're seeing, like we're detecting light, but they won't be able to say like what color it is. So in a sense, the kind of peripheral vision that you have is basically black and white vision. It just, is there visible light or not? Then inside the main kind of center of the back of your eye, you've got a bunch of cells that can detect red light. So these are cones that primarily focus on red light, and they're kind of, all scattered around. Then you've got cones that detect blue light, kind of all scattered around. So a bunch of cones that can detect blue light. And there's roughly an equal number of red and blue cones. Whoops. But as far as green cones go, there's actually about twice as many green cones. So we're really good, comparatively speaking, at detecting green light compared to red and blue. There's just a lot more green cones on the typical eye. So we've got something like this. So then when light hits our eye, if it's, say, this, I'm going to make a yellow triangle here. So if there's a yellow triangle you're looking at, that yellow light lands on the eye and then activates these cones in a certain way, and then basically your brain knows, oh, there's no light hitting everything around, just in this triangular region, so therefore we must be seeing a triangle. Now, what actually happens with the different types of light is if we have our red cones, there's a curve that looks like this. The green is going to be a curve that looks like this, and the blue is going to be a curve that looks like this. And this shows the sensitivity of the light, or of your eyes, to certain frequencies. So in other words, if a frequency right here hits your eye, then the red cones are going to send a big signal. And that means it's because it's red light. If this signal hits your eye, then the green cones are going to send a huge signal, like really strong signal. If it's here, the blue cones will send a strong signal. But you'll notice they overlap. So if you had, like I said, this green frequency, some of the blue cones will also light up, some of the red cones will also light up. And then your brain takes all that information and it assumes it's all kind of one type of color, and it makes up a color in your brain. So in this case, if the greens are really strong and the reds and blues are a little bit, your brain says, oh, it must be green light, because it knows that red will sometimes light up a little bit with green and blue will sometimes light up a little with blue. Where that gets interesting is you have stuff like here, where if red and green are both lighting up but neither of them very strong, then the brain says, oh, it must be this sort of in-between frequency of light, which our brain understands as yellow. Likewise, if you're down here, you get that kind of in-between green and blue, and you get that cyan color, that kind of really kind of bright-ish blue color. And what gets interesting is our brain assumes that everything is sort of one color. Everything has one color, so one color of light. But sometimes multiple colors might be coming towards our eyes. So for example, if something is giving off red and blue light at the same time, our brain makes up some fake color that doesn't actually exist as its own type of light, and that's what we see as magenta. So magenta is what happens when red and blue both light up, but green does not in our brain, or on our on our cones. So if red cones and blue cones are both like really strong, that's where we get that really pinky, purpley magenta color. So there's no way to make that color of light. It's only from a mix of red and blue hitting our eye and interpreting that. Now you might know a connection to this if you've ever looked really close at a TV or a monitor or something. Because we know that our brains only detect red, green, and blue, it doesn't make sense to have a computer screen give off other colors of light, because our brains are just going to see them as a mix of red, green, and blue. So that's why TVs and monitors and all of that just give off mixtures of red, green, and blue to kind of trick our brains into thinking there's these other colors. So all this yellow that I'm writing, if you zoomed in really close to your computer screen right now or your phone screen or whatever you're watching on, you would see that it's just red and green pixels lighting up and no blue. Whereas if you look at the green, that's going to be mostly green pixels, the red, mostly red, blue, mostly blue. But that's sort of the mix of all of these things. So then we get other colors like white and black are just from if everything's lighting up kind of equal strength, our brain interprets that as white. And then if it's really strong, it's white. If they're all really weak, it's black or dark gray, and then kind of in between. So our brain sees whites and grays when we have kind of equal activation of everything. Things like browns or other colors are just from mixing these different activations. So that kind of wraps up how we see and what's going on there. This is useful just to kind of know what's going on. It's interesting for how our brains work.